तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Last few lectures we were discussing about the biological treatment of wastewater. We have seen what all are the different process modifications of activated sludge. We have discussed in details about pond systems, and we have also seen that the facultative pond is the one which is most commonly used in wastewater treatment systems, and we have seen how to design the pond systems and all in detail. But the most common thing whatever we have discussed till now is all those processes were attached growth suspended growth systems. So today we will discuss about attached growth systems which are commonly used in wastewater treatment, that too in aerobic conditions. So coming to the attached growth systems, the most commonly used one in wastewater treatment are trickling filters and rotating biological conductors. There are other few systems which is not so commonly used, but it is coming up in wastewater treatment processes. They are fluidized bed attached systems and submerged systems. So these two systems are commonly used in aerobic system as well as in anaerobic system. So today we will be concentrating on attached systems which are commonly used in aerobic systems. So coming to the aerobic system, as I have already told, trickling filters and rotating biological conductors are most commonly used, and in anaerobic systems, anaerobic filters, anaerobic fluidized bed reactors etc. are being used, and in anoxic process we can go for this denitrification system in attached growth system also. We have discussed nitrification and denitrification in detail in suspended growth systems. So first we will discuss what is the biology of the attached growth system. So this shows somewhat a schematic picture of the system biology. It consists of heterogeneous microorganisms, and you have a solid medium on which the microorganisms are growing. So this is the solid medium and this is the biofilm, and we can see that this is the wastewater film whatever is passing through the trickling filter, and this is the air. Air is passing along with the liquid. So how the reactions are taking place in the biotrickling filter. So the term itself is not giving the actual picture of the treatment system. Though we are calling it as a biotrickling filter, in the filtration part is very negligible. The treatment is occurring because of biological action. The waste whatever is present in the water will be penetrating to the liquid film. From that one it will be coming to the biological film, and biological action will be taking place, and as a result the organic material will be converted into carbon dioxide and water. So because of this organic matter conversion, what will happen? As we have already discussed, more and more cells will be generated. So the biofilm thickness in the solid support will be increasing with respect to time. And what will happen to the oxygen diffusion and the substrate diffusion? So oxygen diffusion and substrate diffusion through the film will be limited. So as a result we will be getting an aerobic zone in the beginning, or which is in contact with the liquid film, and an anaerobic zone which is in contact with the solid surface. How it is happening? Because the air is available or oxygen is available to the system because of the dissolved oxygen whatever is present in the wastewater, as well as when air moves through the biotrickling filter, it comes in contact with the liquid film, and because of that contact some oxygen will be diffusing from the gas phase to the liquid phase. So the thickness of the aerobic zone, I told you the biofilm will be having an aerobic zone and anaerobic zone. The thickness of the aerobic zone will depends upon the oxygen transfer as well as the organic concentration of the wastewater. And the factors that affect the oxygen transfer are: one, the overall oxygen transfer coefficient. Second one, what is the concentration of oxygen in the solid liquid interface. If the oxygen concentration in the solid liquid interface is very high, naturally high concentration gradient will be available between the liquid film as well as the biofilm. So naturally more oxygen transfer will be taking place. And the next one is how much is the dissolved oxygen present in the liquid film. That is also important, which decides what is the amount of oxygen getting transferred to the system. And another factor which affect the aerobic zone or anaerobic zone thickness is the organic matter penetration into the biofilm, because if more and more organic matter penetrates to the biofilm, naturally the microorganism requires more oxygen to transfer them. The organic matter penetration also depending upon the flow rate of the wastewater and the organic concentration of or organic loading whatever we are applying to the biotrickling filter. If the wastewater is having high BOD or high COD, naturally the organic matter penetration will be very high to the system. The next one is how much is the biodegradability of the organic matter. Though the organic matter penetrates at a faster rate, if it is not biodegradable, then what will happen? The microorganisms may not be able to utilize it in a proper way. So naturally the oxygen utilization rate will be less, so the aerobic zone thickness will be high. And another one is the substrate utilization rate or the degradation rate of the organic matter whatever is penetrated through the biofilm. If the degradation rate or the specific substrate utilization rate is very high, naturally a corresponding amount of oxygen should be available, then only the degradation will be taking place. So these are the factors which decides the aerobic zone thickness and the anaerobic zone thickness. If the aerobic zone thickness is less, naturally the anaerobic zone whatever is present, it will be having a higher thickness. And usually whenever we talk about the attached dose systems, the thickness of the biofilm varies from 1 to 3 millimeter, because if the thickness is higher, there are various problems. One is, okay, the thickness is more, the porosity is limited, so clogging of the biofilter will be taking place. So it will not be allowing the penetration of liquid as well as air through the biotrickling filter. And another one is because of the flowing of water, some shear stress will be developed and it will be shearing the biofilm if the thickness is very high. And another factor is what will happen if the thickness of the biofilm is very high, the penetration of organic matter is limited. So what will happen to the microorganism whichever is present in the extreme end of the biofilm or the biomass whatever is very close to the solid medium? The food availability will be limited, and as the thickness of the biofilm increases, more and more food will be available in the biofilm which is in contact with the liquid. So there more oxygen, more organic matter etc. will be available, but as the organic matter penetrates through the biofilm, as it comes to the extreme end or the one which is staying near the solid medium, by that time all other microorganisms whatever is present till that will be utilizing the organic matter, and as a result the microorganisms whatever is staying near the solid will be deprived of food. So how can they survive? They will be undergoing endogenous respiration or auto-oxidation. So as a result what will happen? There will not be any microorganism in the layer which is very close to the solid medium. So naturally the biofilm loses its attachment capacity and it will be coming out of the biotrickling filter or the supporting medium. So in the system the thickness of the biomass in the attached medium is controlled by itself by the diffusivity of the oxygen as well as the organic matter, and because of the food limitation endogenous respiration takes place and it will be getting detached from the system. So sloughing of the biomass will be taking place and this will be coming along with the treated effluent. So that is what I have represented here in this picture. So this is the solid medium and this is the biofilm, and we can see that this is the wastewater film because the biofilm is there. So naturally the liquid is passing in this direction. So there will be always a film attached to the biofilm, a film of water attached to the biofilm, and this is the air space and air will be flowing or moving in this direction. So what is happening? whatever is the dissolved oxygen present in the wastewater, that is entering into the biofilm. You can see that this is the oxygen penetration. Oxygen penetration can take place both from the wastewater film as well as from the air. Air, it first enters in the wastewater, then from this film it will be entering into the biofilm, and some dissolved organics, as it passes, it will be entering into the biofilm. So what is happening? Here we can see that lot of oxygen is available in this region. So this region is working under aerobic conditions. As we goes towards this side, what will happen? The oxygen availability will be limited, because whatever oxygen available will be utilized by the microorganisms here. So as we goes here, the oxygen availability will be less. So this film will be in anaerobic conditions, and if the thickness of this film increases further, what will happen? This dissolved organic penetration, that also will be limited. So what will happen? The microorganisms here will be utilizing a portion of the organic matter, and the concentration of the organic matter will be reducing with respect to the distance. So microorganisms here may not be getting enough food. So as a result, it will be undergoing endogenous respiration, and once the complete endogenous respiration of the layer here takes place, the entire biofilm will be peeling off from the supporting medium, that is known as sloughing. So now we will see how the organic matter is getting removed in the system. The rate of organic matter removal is depending upon the wastewater flow rate and organic loading rate, rate of diffusivity of food and oxygen into the biofilm, and the temperature. How these parameters are very important. Okay, as we discussed, if the wastewater flow rate and organic loading rates are high, then what will happen? Naturally, the penetration of organic matter from the liquid film to the biofilm will be very high. So naturally, if the organic matter is available to the microorganism, then their removal will be at a faster rate. We have seen how the microorganisms are utilizing the organic matter. First, it has to come and get attached to the microbial cells, then it has to enter through the cell wall and go into the cell, then only the metabolic activity will be taking place. As a result, some part will be get converted into carbon dioxide and water because of the catabolic activity, and some part will be consumed for the creation or generation of new cells, which is known as anabolism. So unless the organic matter is available for the microorganism, it will not be getting removed. So that is why if you have a high flow rate and high organic concentration, naturally the penetration of the organic matter will be very high. And any microbial reaction that is temperature dependent, we have already seen that as the temperature increases, the microbial activity will be increasing, and most of the microbial activity, the optimum temperature is around 35 to 37 degrees centigrade in the mesophilic range, and for every 10 degrees centigrade rise in temperature, the microbial activity will be increasing by 100%, and similarly if the temperature is decreased, naturally the microbial activity will be coming down. So that is why the temperature of the system is also very important. So if we can provide a high temperature, that means a temperature above 25 degree throughout the operational period, then the efficiency of the system will be much higher compared to a temperature which is lower than 20 degrees centigrade. Now we will see in detail the trickling filters. Trickling filter is a reactor in which randomly packed solids forms provide surface for microbial growth, and it will have a system for wastewater distribution also. When we select the media for the microbial growth, the most important parameters are specific surface area and porosity. Specific surface area is the amount of surface area of the media that is available for biofilm growth. Porosity is the void space available for passage of wastewater and air. So whenever we select a media for the microbial growth, porosity as well as specific surface area are very important. The reason is, if you have a high specific surface area, the amount of surface or the amount of biofilm present in the system will be very, very high, because the specific surface area, the entire surface, the microbial film will be growing. So as the specific surface area increases, the biofilm area as well as the total volume of biofilm will be increasing. And we all know that in any biological system, the workers are microorganisms. So naturally, if you can provide more microorganisms in the system efficiency will be very, very high. Now coming to the porosity, if the porosity is high, that is the place which holds the wastewater as well as the air. So if you have a high porosity, then you can go for a high hydraulic loading rate. Hydraulic loading rate is the volume of wastewater applied to the system per meter cube per day. That means the meter cube of wastewater applied per meter cube of the reactor per day. That is the hydraulic loading rate. So if the porosity is more, then what will happen? You have more volume inside the reactor which can hold the wastewater. So you can apply more and more water. In practice, the most commonly used solid matrices for the bacterial growth, especially in trickling filter, are crushed stone or slag. So what will happen? The porosity of this media usually varies from 40 to 50%, and specific surface area is around 50 to 60 meter squared per meter cube. So these media are commonly used in trickling filters, which is working under standard condition or standard mode. But there are some other variety of trickling filter which is known as high rate trickling filter. As the name indicates, high rate trickling filter are the one which can be operated at a very high hydraulic loading rate or organic loading rate. So in high rate trickling filters, we go for synthetic supporting media like plastic or some other polymers which is having relatively high specific surface area. In the media commonly used in biotowers or high rate trickling filters is having a specific surface area of 200 meter squared per meter cube and a porosity of around 95%. So from conventional media to this high rate trickling filter media, we can see that the specific surface area is increasing around 3 times and the porosity is also almost double. So naturally the efficiency of the system will be more, or you can treat a large volume of wastewater in a given volume compared to the standard rate trickling filters. So this picture shows a trickling filter. So this is the distribution system. So distribution system consists of few distributing arms. So this is one, and here we can see many nozzles. So the wastewater will be coming out of the nozzle and it will be sprinkled uniformly over the trickling medium surface. So how this distribution system is working in a trickling filter? It is working because of the hydraulic pressure, hydrostatic pressure available here. The wastewater will be coming, and if it can have a hydrostatic pressure of 1 meter of water, then the rotating arm will be rotating by itself because of the hydrostatic pressure. We don't have to give any external power, and this supply of wastewater will be intermittent. So as a result, what will happen? Sometime the wastewater will be trickling over the trickling filter. Say this arm is distributing. Similarly, we can see here also this distributing arm is distributing wastewater. After this distribution, you can see that here the medium is exposed to the air for some time. So the intermittent distribution of wastewater gives a chance for air also to circulate through the medium. So enough oxygen will be available for the degradation of the organic matter by the microorganisms, and that the wastewater will be trickling through the trickling filter, and with respect to time, the organic matter will be getting converted to carbon dioxide, water, and more cells, and most of the cells will be getting attached to the system, and the treated water we have to collect from the bottom of the trickling filter. So we have to provide some collection devices. So these are the collection devices usually used. We can see that this is a concrete material and this is made up of tiles. Okay, these are different systems. We can see that here the openings are there. This will be collecting the wastewater, whatever is trickling through the trickling filter, and from there everything will be collected and going to a secondary treatment system. And as I have already explained, the trickling filter can be divided into 2 or 3 categories: low rate filter, standard or intermediate rate filter, and high rate filter. So, the classification is based upon the hydraulic loading and organic loading rate. In low rate filters or the standard rate filters, the hydraulic loading rate represented as meter cube of wastewater per meter squared of filter area per day varies from 1 to 4, whereas intermediate rate filter it varies from 4 to 10, and in high rate filter it varies from 10 to 40. That means the high rate filter can treat around 10 times more wastewater compared to a low rate or a standard rate trickling filter. And organic loading rate, it is expressed in terms of kilogram per meter cube per day. Organic loading rate varies from 0.08 to 0.32 in low rate or standard rate trickling filter, and in intermediate rate filter it is 0.24 to 0.48, and in high rate it is 0.3 to 1. So, we can see that if you go for high rate filter, we can increase the hydraulic loading as well as the organic loading rate. And the depth of the medium in low rate filter it is varying from 1.5 to 3 meter, intermediate it is 1.25 to 2.5, and high rate filter it varies from 1 to 2 meters. Sometimes in bio towers and all we can go for a depth of even 10 meters. And recirculation ratio, low rate filter it is 0, and intermediate rate filter it varies from 0 to 1, and high rate filter it varies from 1.1 to 3 or 2 to 3. And filter media we have already seen. In standard rate filter we usually use crushed stones or slag. In the intermediate filter also the same thing, but in high rate filter we use synthetic material usually. And the power requirement, standard rate filter requires less power because the recirculation is not there much, and intermediate it varies from 2 to 8 kilowatt per 10 raised to 3 meter cube of water, and in high rate it varies from 6 to 10 kilowatts per 10 raised to 3 or 1000 meter cube of water. And another one, the nuisance is filter flies. In low rate filters, the filter flies or the cycoda, that is the flies usually found, those are many. In intermediate rate filters they are intermediate, not many are there, but in high rate filter very few flies are seen. And coming to the sloughing, that means how the sludge is getting removed from the system. Low rate filters it is intermittent, intermediate rate filter it is intermittent, and coming to the high rate filter the sloughing is continuous. And dosing intervals for low rate filter it is not more than 5 minutes, and intermediate rate filter 15 to 60 seconds, and high rate filter not more than 15 seconds. And effluent here in standard rate or low rate filter it is usually fully nitrified, that means it does not require any further treatment. And intermediate rate filter it is partially nitrified, and in high rate filter if the organic loading rate is low then we get nitrified liquid. If the loading rate is very high then we will not be getting nitrified effluents. So, in trickling filter we have seen the organic loading rate as well as the hydraulic loading rate. But coming to the hydraulic loading rate, in trickling filter the hydraulic loading rate is very important, because I have already discussed how the distribution of wastewater is taking place in the trickling filter. It is because of the hydrostatic pressure available in the distributing arm. So, if enough hydraulic loading rate is not practiced, what will happen? The hydrostatic pressure available will not be sufficient for the movement of the rotating arm. So, in such cases we have to supply power externally. But if the hydrostatic pressure is sufficient, then what we can do, that pressure itself will be taking care of the wastewater distribution in the trickling filter at the specified intervals. So, the hydraulic loading rate is very important. And in trickling filter also we use recirculation, but the recirculation of trickling filter is entirely different from that of activated sludge process. In activated sludge process we are recirculating to increase the biomass concentration in the aeration tank, So we recirculate the settling sludge from the secondary sedimentation tank to the aeration tank of the activated sludge process. So the recirculation is to maintain a high concentration of mixed liquid suspended solids in the aeration tank, because that will definitely increase the efficiency of the system. Now coming to the trickling filter, we know that the biomass is growing attached to the medium. So in the system will be having a high concentration of biomass always. So we need not supply biomass to the system. So what is the purpose of recirculation in the biotrickling filter? One is to provide enough hydrostatic pressure to the distributing arm, because if the hydraulic loading is not sufficient, what will happen? The distribution system will not be operating properly. So to get enough hydrostatic pressure, we recirculate the treated effluent from the secondary sedimentation tank, because in trickling filter also we need to have a secondary sedimentation tank. The reason is a portion of the biomass, whatever is attached to the system, it will be sloughing off and coming to the effluent. So if we allow the effluent to go just like that, what will happen? This slough biomass will be going along with the treated effluent, and naturally the suspended solid concentration as well as the COD of the system will be very high, or the treatment efficiency will not be meeting the required standards. So we have to provide a secondary sedimentation tank. So the recirculation is from the effluent of the secondary sedimentation tank, not from the settled sludge. So that is the major difference in recirculation between an activated sludge process and a trickling filter. Okay, here we are recirculating the effluent, not the sludge. And one more reason for the recirculation is that with one pass, most of the time the COD will not be getting removed completely. So if you pass again and again, it will be getting more contact time, and the microorganism will be getting more time to degrade the organic matter. So to increase the treatment efficiency also, we recirculate the waste to the system, and the recirculation system can be practiced in many different ways, either directly before going to the secondary sedimentation tank or after going to the secondary sedimentation tank. And in biotrickling filters, we can even put many biotrickling filters in series instead of providing a single filter. If we can provide a series of filters, it will increase the efficiency of the system. The reason is the effective depth of the biotrickling filter will be increasing. Because of practical problem, in a single biotrickling filter, we cannot provide a depth more than 2 to 3 meters. But if you provide a series of biotrickling filters, what will happen? One will be giving a particular efficiency. From that one, that effluent is going to a second trickling filter, that will be removing a considerable amount of organic matter, whatever is present in the system. So as a result, what will happen? The effluent coming out of the series of treatment unit will be having better quality compared to a single unit. So whatever I have discussed now, it is written here. The hydraulic loading rate is important, because reaction of water, based upon that one, the distribution system is working. If wastewater is not sufficient, treated water is used to provide sufficient reaction power, and no cellular recycle is required, only treated water is recycled. Theta C is always greater than theta. Theta is the hydraulic retention time because of attached growth, because whatever is the biomass generated in the system, most of them is staying in the system itself. So biological sludge retention time in an attached growth system is always much higher than the hydraulic retention time. So now we will see how to design a trickling filter. So there is no theoretical approach available for the design of trickling filters. Mostly empirical equations are used for the design of trickling filter. That means in the field many biotrickling filter or pilot trickling filters will be available based upon their performance and based upon the volume, flow rate, etc. And we know what is the influent BOD or COD and what is the effluent BOD, COD. Based upon that one, the design criteria is developed. So the most commonly used approach for the design of trickling filter is the NRC equations. That means the National Research Council equations. So this is the formula. If you want to design the first stage of a trickling filter, we can use E1 is equal to the efficiency of the first stage is equal to 1 by 1 plus 0.007 into square root of W by V into F, okay, where E1 is the BOD removal efficiency from the filter, the first filter, and W is BOD applied, that means kilogram per day without any recycle, and V is the volume of the filter in meter cube, and F is equal to 1 for no recycle. So we can, if we know the BOD applied per day to the biofilter or biotrickling filter and the volume of the filter, then we can find out what is the efficiency of the system. And if the recirculation is there, that means the system we are recirculating the wastewater, F equal to 1 plus R divided by 1 plus 1 minus delta into R all squared, where R is the recirculation ratio. And we can see here one term delta is coming. So delta is nothing but the weightage factor included to compensate for the assumption of the rate of utilization of substrate decreases with each pass through the biofilter. So what does this delta means? That means in the first cycle of the wastewater flow, what will happen? The organic matter will be penetrating through the biofilm and the microorganisms will be utilizing the organic matter, but the utilization rate will be depending upon the biodegradability of the waste. So naturally in the first cycle or the first pass itself, the highly biodegradable organic matter will be getting removed from the system, and the wastewater whatever is less degradable, it will be coming out of the biofilter and it is again getting recirculated through the biotrickling filter. So what will happen? Definitely in the second cycle, the removal efficiency will not be so high. The reason is highly biodegradable organic matter is removed in the first cycle, and in the second cycle, okay, less biodegradable organic matter is present. So even though we are keeping the same organic matter loading rate and same volume of the filter, in the second cycle the efficiency will be less because of the less biodegradable material present in the system. If you want to take care of that one, we have to include some factors. So that is what this delta is doing. So delta will take care of the decrease in substrate utilization rate because of the recirculation. So this is how the recirculation, I told you in a trickling filter we recirculate the water. So we will be having a primary sedimentation tank. So this is essential. The reason is the wastewater will be having so much of suspended solids. So if you don't remove the suspended solids, it will be going to the trickling filter and get accumulated in the pores of the trickling filter, and clogging of the trickling filter can take place. So that's why it is always advisable to have a primary sedimentation tank before the trickling filter. So here what is happening, the trickling filter is here, whatever is the effluent coming out, it is not even going to the secondary sedimentation tank. Before that it is getting recycled and a portion will be going to the secondary sedimentation tank, and after the sludge settling, the treated effluent is going out. And this is a multiple stage trickling filter, primary sedimentation tank, and this is the trickling filter. Recirculation, this recirculation can be either from here or we can have the recirculation like this, and this is the second trickling filter and recirculation, and this is the secondary sedimentation tank. And here also, instead of recirculating from here, we can recirculate from here also. But many studies have shown that either we recirculate from here or after secondary sedimentation, if you recirculate also, there is not much change in the efficiency of the system. So as well recirculate from here so that we can reduce the volume of the secondary sedimentation tank. So now we will see what is the removal efficiency if you go for a series of biotrickling filter. So first filter we have seen how to find out the efficiency. So if you want to find out the efficiency of the second filter, we can use this formula. E2 is equal to 1 by 1 plus 0.0071 divided by 1 minus E1 into W2 by V2 into F. So E1 is nothing but the efficiency of the first biotrickling filter, and W2 is the BOD applied to the second stage given in kilograms per day, and V2 is the volume of second stage in meter cube, and F is the factor which we have already explained or we have seen. Okay, if recirculation is there, what is the F value? If recirculation is not there, what is the F value? So if we have a series of biotrickling filter, we can find out E1, E2, E3 like that, and the total removal we can find out, that will be the sum of the efficiency of 1, 2, 3, etc. The thing is, we cannot just add up the efficiencies because the first one will be removing 80%. So the concentration coming to the second system will be only 20% of the initial concentration. From that 20%, 20 of the initial, 80% will be removing in the second one. So based upon that one, we can find out what is the total efficiency. So depending upon what is the effluent requirement, effluent quality requirement, we can decide whether we can go for a single stage biotrickling filter or we have to go for a series of biotrickling filter. Nowadays, okay, people are not going for the standard rate biotrickling filter because the organic loading is limited and the hydraulic loading rate is limited. So if you want to reduce the volume of the biotrickling unit, okay, we have to have a very high hydraulic loading rate and an organic loading rate. So nowadays the biotowers are coming up. So biotowers are nothing but deep trickling filters, and here the attached medium whatever we are using is lightweight modular media. So we can go up to 12 meter height. So it is, biotowers are not nothing but a high rate biotrickling filter with a height of 10 to 12 meters. So how can, so this shows a biotower. So here we can see the influent is coming and this is the primary clarifier. So here all the suspended solids from the wastewater is being removed, and here the wastewater whatever is coming from the primary sediment clarifier is pumped to the biotower, and this is the biotower. So the treated water is collected here, it is going to the secondary clarifier and effluent is going out after the treatment. So we can have the recycling either from here, so we can see the effluent recycling, and here whatever is the sludge in the secondary clarifier, that is collected along with the sludge from the primary clarifier and it is going for further treatment. And if you don't want to have this type of a recycling, we can even have a recycling from here itself. Instead of increasing the secondary sedimentation tank volume, we can even have a alternative recycling from here. So it's all depending upon how we want to operate the system, but either this recycling or this recycling, it is not going to affect the performance of the system drastically. And this figure shows the typically used synthetic media which is serving as the support media. So here you can see that it is a synthetic media, it is having lot of surface area for the growth of the microorganism. You can see here all the pores and it is running throughout the media. So the porosity of this medium will be around 90 to 95% of the total volume, and the specific surface area is around 200 meter squared per meter cube. So you can imagine how much biomass this type of supporting media can hold. Now we will see how to design these biotowers. Usually it is being designed based upon Eckernfelder's equation. So if you know what is the effluent quality we have to get from the biotower, that means SC. So this is depending upon the effluent discharge standard, and S0 is the BOD, ultimate BOD of the wastewater whatever is coming to the system. So SC by S0 is nothing but E raised to minus K into D by Q raised to N, where SC is the effluent substrate concentration, either BOD 5 or BOD U in milligrams per liter, and S0 is the influent substrate concentration or BOD 5 in milligrams per liter, and D is the depth of the medium. Q is nothing but the hydraulic loading rate, that means meter cube per meter square per minute, or you can put it in terms of days also depending upon the unit of this K value. And K is nothing but treatability constant relating to the wastewater and the medium characteristics. So this K will be taking care of the biomass concentration in the media as well as how efficient the biomass is to remove the organic matter present in the system, or it will be taking care of the biomass concentration as well as the specific substrate utilization rate. And n is a coefficient related to the medium characteristics, and this k value, that means the rate of substrate utilization, is a function of temperature. So as the temperature increases, this value also will be varying, or as the temperature increases, k value also will be increasing. So we can find out kT at any temperature if we know the k value at 20 degrees centigrade using this formula, K20 into 1.035 raised to T minus 20, where T is the temperature or the operating condition temperature. And if we have a multiple unit or recirculation, then we can find out what is the SE by SA value. The first one is without recirculation, and this is the with recirculation, how the efficiency is. That is equal to E raised to minus Kn by Q raised to n divided by 1 plus R minus R into E raised to minus K into D by Q raised to n. So this will be taking care of the recirculation. Because of the recirculation, what is the dilution coming into picture, as well as how the biodegradability is reducing with each pass of the wastewater. And here Si is nothing but S0 plus R into Se by 1 plus R, because the loading or the total concentration of BOD going to the system will be different from whatever is coming in the wastewater, because some sort of dilution will be taking place. So that is what we are calculating here. Si is what is the applied BOD, that is equal to S0 plus R into Se by 1 plus R, where R is the ratio of the recycled flow to the influent flow. So till now we were discussing about trickling filter. There are other attached flow systems also which is commonly used in wastewater treatment. Another one is rotating biological conductors. So here what is happening is, you will be having a series of discs partially immersed in the wastewater, and it will be rotating at a speed of 1 to 2 RPM, okay, because all the discs will be connected to a shaft and it will be rotating at a particular speed. So what will happen with respect to time, different portions of the disc will be getting exposed to the air. So oxygen will be available for the microorganisms for the removal of organic matter. So this shows, this is the influent coming, and you have a primary clarifier. The water from the, or the wastewater from the primary clarifier is entering in the rotating biological conductors. So a series of discs arranged in a shaft, okay. Either we can have a single shaft or we can provide a series of shaft also. So this is a 4 units system. So the wastewater will be flowing in this direction and the disc will be rotating in this direction. So what will happen? In this disc, the microorganisms will be growing, and this is the water level. So only a portion of the disc will be exposed to the wastewater at a time, and remaining portion of the disc with the biomass will be getting exposed to the atmosphere. So there will be oxygen transfer. So enough oxygen will be getting transferred to the microorganism for the degradation of the organic matter. And here also some biomass will be coming out. So there is a secondary clarifier which removes the biomass whatever is coming along with the treated effluent, and this is the treated effluent. So this shows the clear photograph. So now we will go into the details of the process. So if you take a shaft, so it is something like that, and you will be having many discs attached to the shaft. So there will be some spacing between this disc. So a series of discs will be arranged like that. Usually the disc diameter will be varying from 3 to 4 meters depending upon the wastewater flow rate and what is the capacity we need to design. Or if you want to take the other view, we will get like this, okay. This is the unit and the wastewater will be there up to this level. That means around 40% of the disc will be immersed in the wastewater. So a flow rate of Q is coming and S0 is the initial BOD of the wastewater, and this is the disc. So what is happening? This is the center of the disc and this much portion will be immersed in the wastewater. So naturally the biomass will be growing in this circle. So this portion is not getting exposed to the wastewater, so there will not be any growth of biomass. So you will be getting a biomass growth like this ring shaped biomass growth, okay. And here also this is the wastewater, so definitely because the oxygen is getting transferred from the atmosphere to this wastewater, so some growth will be taking in the suspended system also, but the BOD removal or the organic matter removal in this suspended system will be much negligible or much less compared to the organic matter removal by the attached film. The reason is here we give very little residence time in the order of 20 to 30 minutes, so the biomass will not be getting enough time for the removal of organic matter. And finally what will happen, the treated effluent is coming out Q into SC, and this B represent the biofilm. So if you want to find out what is happening in the system, ADC is the adsorption of substrate on biofilm. So which is the ADC portion? If you put here, this is B, so we can put like this, okay. From here to here, this on, okay, what will happen? The adsorption of the organic matter will be taking place in the biofilm because this portion is immersed in the wastewater. And CBA, assimilation, CBA is this portion, CBA. So this is CBA, this is A, this is D and this is C. So CBA, the assimilation of the microorganism will be taking place as well as the oxygen transfer will be taking place here. So ADC, adsorption of substrate on biofilm, and CBA, assimilation of substrate plus growth of microorganism plus atmospheric transfer of oxygen. So like that the biofilm will be growing and it will be removing the organic matter as well as more and more cells will be generated. So because of this process there is no need of any aeration. Substrate removal by attached growth system as well as suspended growth system is taking place, and substrate utilization by the suspended system is negligible because HRT is only 20 to 30 minutes. And advantages of this system are short HRT due to high biomass concentration, usually 20 to 40 minutes, and capable of handling wide range of flow, no sludge recycling is required, and it is able to handle different types of loading. So now we will see how to find out how to do the design. So this is a typical disc. So you have seen that the biomass is growing only this area, and this Q is the flow rate, S0 is the initial BOD, SC is the effluent BOD, and this is the biomass growing area. So if you want to make the mass balance, how can we do it? Net rate of change in amount of substrate within the reactor, that is equal to rate at which the substrate enters the reactor minus rate at which substrate disappears from the reactor. So how can we find out the rate at which the substrate is entering into the system and rate at which the substrate is removing from the system? The rate at which substrate is entering in the system is nothing but Q into S0, where Q is the flow rate and S0 is the initial BOD of the wastewater. And how the substrate is getting removed from the system, that is equal to ds by Et UA into VA plus ds by dt US into VS plus Q into SA. So this is the substrate utilized by the attached growth microorganism. Whatever the microorganism attached to the disc, so the organic matter whatever is removed by the attached growth system, and this is the biomass, this is the substrate whatever is utilized by the suspended growth system, and Vs is the volume of the suspended growing system, Va is the volume of the attached growing system, and Q into SC, Q is the flow rate, SC is the effluent BOD. So that is what I have given here, ds by dt UA, rate of substrate utilization per unit volume of attached growth, and ds by dt US, rate of substrate utilization per unit volume of suspended growth, and Va, volume of active attached biological growth, Vs, liquid volume of reactor, S0, influent substrate concentration, and SC, effluent substrate concentration. And if energy of maintenance is neglected, so we are assuming that no energy is used for the maintenance, then we can write like this dx by dt. That means the rate of change in biomass concentration, that is equal to yt into ds by dtu. That means yield coefficient into rate of change of substrate concentration. So we can find out what is the rate of change of biomass in attached growth system and what is the rate of change of substrate in suspended growth system. One is Ya into ds by dt Ua and Ys into ds by dt Us. And we have seen dx by dt is absolute growth rate of attached biomass and Ya is theoretical yield coefficient. Now we can write like this, dx by dt by Ya is ds by dt Ua and dx by dt Se by Ys equal to ds by dt Us. Just readjusting the equation. And if you divide both by xf, that means biomass concentration in the fixed film, dx by dt into xf by Ya. Okay, this term dx by dt by xf, we have already seen that specific growth rate that we can replace by mu a, and this xf will be coming here by Ya, which is nothing but ds by dt. We are rearranging the terms. Similarly here also, if you divide by xs and multiply by xs, we will be getting mu s into xs by Ys, which is equal to ds by dt into Us, where xs is the active biomass per unit volume of attached growth and xs is the active biomass per unit volume of suspended growth system. So your final equation will come like this, ds by dt in the total reactor is equal to q into S naught, that is coming in, minus q into Se, this is going out, minus mu a into xf by Ya into Va minus mu s into xs by Ys into Vs. So this is the substrate utilized by the attached growth system and the substrate utilized by the suspended growth system. And now we will find out what is the Va. So how can we find out the Va? So we have to find out what is the area on which the biomass is growing. A is nothing but 2 into n is the number of discs into pi into r naught square minus Ru squared. This Ru is the area which is not exposed to the wastewater. So that is what I have written here. N is number of discs, R naught total disc radius, Ru unsubmerged disc radius. So you will be getting total area on which the biomass is growing, and if you know the thickness of the biomass, we will be getting the volume. So that is what I have written here. And at steady state, the net change of biomass concentration or substrate concentration is 0. So we can write like this. This is the steady state condition. Q into S naught minus Q into Sc minus mu a into x into Ya into, this is D, the thickness of the biomass, into total area minus, this is the biomass concentration because of the, or the substrate removal because of the attached growth, where V is the liquid volume of the reactor. And we also know that mu is equal to mu max S by Ks plus S, and S is nothing but Sc. So that is what here we have written, Q into S naught minus Q into Sc into mu max A xf d 2 pi n into R naught squared minus Ru squared into Sc by Ks plus Sc, and the other term we are leaving like that. So here we are neglecting the contribution by the suspended growth system, because we have already seen that in the suspended growth system the time available is very less, so the removal will be very less. So if you want to find out what is the BOD removed, that is equal to Q into S naught minus Sc, that will be equal to 2 into mu max into area by Ya into n into pi into dx Sf R naught squared minus Ru squared into Sc by Ks plus Sc, and you know that this Sc is very negligible. So you will be getting the equation like this, and we can replace this entire term with a constant P, which is equal to 2 into mu max A into xf into D by Ya. So this will be depending upon the that rotating biofilter, and this will be a parameter decided by the system. So if you replace all these parameters with a factor P, it will be taking care of total cross section, total area on which the biomass is growing, the thickness, then Ya and mu max are the constants. Then we will be getting the equation like this, Q into S naught minus Sc, that means the total organic matter removed in the system is equal to Q into P into N into pi into R squared R naught squared minus RU squared into SC by Ks plus SC, or we can write like this, take this term this side and take the inverse, then 1 by P plus Ks by P into SC is equal to 2N into pi into R naught squared minus RU squared by Q into S naught by SC. So, if you want to find out what is the P value for a system, we can do some batch experiments in the lab and we can find out this is 1 by SC and this term is equal to 2 into N, number of the disk, into pi into R naught squared minus RU squared into Q into S naught minus SC. All these terms are known to us. Then if you plot this one, we will be getting a line like this. So, this one will be giving you 1 by P and this one will give you Ks by P. From this one we can find out what is the half saturation constant and what is the P value for the system. So, this is the way we usually design the rotating biological contactors. So, we will be knowing the biokinetic parameters. So, using the biokinetic parameters, we can find out what is the BOD removal the system can have. So, based upon that one we can find out what is the number of disks we can provide. So, either you provide the disk in a series or provide a series of disks. So, that is the rotating biological filters. So, nowadays active biofilters are also being used, that is a combination of RBC plus activated sludge process, that will be improving the efficiency considerably. So, we have talked about attached flow systems which is commonly used in wastewater treatment processes. One is trickling filter, and in trickling filter itself we can go for high rate trickling filters and standard rate trickling filters, and RBC we have seen how to design it, and nowadays activated RBCs are being used. It is a combination of rotating biological filters as well as activated sludge process. Next class we will discuss about anaerobic process.